Predicting the shape of molecules. Let's take a molecule with an atom and two bonds. You've got two electron pairs on each side bonded to the central atom. And this molecule will be a straight line or a linear molecule. And the bond angles are 180 degrees. If we try and nudge those bonds closer together, they just repel back into this straight shape. If you try and add a third bond, so you've got three pairs of electrons around that centre, we'll get a trigonal planar shape. That word planar means flat. Trigonal means three, so there's three bonds and they're in that kind of flat shape and they repel to 120 degrees in the trigonal planar molecule. So if we go and add an extra bonding pair, so we've now got four bonding pairs of electrons, they repel to a slightly odd angle of 109.5 degrees. And we call this shape tetrahedral. And all of these bonds are equivalent, so if we shift the molecule around, it just looks the same whichever angle we look at it from. So this would be something like methane, for example, where carbon has four hydrogens joined to it, and that forms four bonds. There are no lone pairs on the middle, so they all repel to 109.5 degrees, and methane would be a tetrahedral molecule. So if we go and add an extra bond to this, that would give us five bonding pairs around the middle. And this is quite an odd shape. Have a look at what happens if we put an extra bond into this. This is called Trigonal Bi-Pyramidal. We've now got five bonding pairs around the centre, and do you see those three bonds around the middle of the molecule? One goes up, one goes down, and then you've got three around the middle. So the three around the middle are at 90 degrees to the ones facing up and down. And if we flip the molecule on this end and look at it, we've got 120 degree bond angles. So there's two sets of bond angles, 90 and 120 degrees in the trigonal bipyramidal molecule. So that's the trigonal bipyramidal shape. Take an extra bond, pop it in, and that gives us an interesting shape called octahedral. And all of the bonds now repel to 90 degrees. So when the bond angles are 90 degrees, you've got six bonding pairs of electrons around the middle. We call it octahedral. So this forms a basis for working out the shapes of molecules, but sometimes you can have lone pairs of electrons too. And the thing to bear in mind with lone pairs of electrons is they repel a bit more than bonding pairs, so the bond angles are just reduced slightly when we put lone pairs into our molecules. So take iodine pentafluoride as an example, IF5. Let's see what we'd have. Remember, iodine in the middle would have 7 electrons in its valence shell. 5 of them form bonds, and that leaves a pair of electrons, so you've got a lone pair, and we get this kind of shape. So that's basically a square-based pyramid. IF5 is a square-based pyramidal molecule, and the bond angles are just slightly under 90 degrees. So let's have a look at what happens if we have 4 bonding pairs and 2 lone pairs. So something like xenon tetrafluoride would be like this. The bonding pairs sit on opposite sides, leaving the atoms in the middle being bonded into a square, and it's flat, so it's square planar. That'll be a square planar molecule. And the way that you draw it is you draw the wedges to show the atoms coming towards you. Hashes show atoms going away from you. And you put the lone pairs above and below that square-based planar molecule. Okay? So that'd be xenon tetrafluoride. Let's have a look at what happens if we have sulfur tetrafluoride this time. So sulfur has 6 electrons in its valence shell. If 4 of them are used up in covalent bonds, that leaves an electron pair at the top. And we get a weird shape. This is called the seesaw shape. And we can draw it like this, the wedge showing the bond coming towards you, the hash shows a bond going away from you. And then we'll pop all of the fluorines in and put the electron pairs on the fluorines as well. So that's the kind of shape we get in something like sulfur tetrafluoride. So what happens if we have 3 bonding pairs and 2 lone pairs? Well, bromine trifluoride would be an example of something like that. So let's have a look at the next one. Okay, so we've got 1, 2, 3 bonding pairs, 2 lone pairs, and this is bromine trifluoride. The bonds repel to 90 degrees and they kind of make a T-shape. So this is actually called a T-shaped molecule, BrF3, and we've got 2 lone pairs on the bromine. So one there and one there, that's how you draw that. And that's bromine trifluoride, it's a T-shaped molecule, BrF3. Okay, let's have a look at what happens if we have 3 bonding pairs and 1 lone pair of electrons. So this would be something like ammonia, for example, NH3. So nitrogen has 5 electrons in its valence shell, 3 of them are using the covalent bonds, that leaves a pair on the top. So you get a molecule that looks like this. It's based on the tetrahedral shape, which repelled to 109 degrees, pushed down a bit more to about 107 degrees by that lone pair. And that's called a pyramidal shaped molecule. So the shape of this molecule is pyramidal. Ammonia is a pyramidal molecule, and we usually draw the lone pair up there on the top. What happens if we have 2 bonding pairs and 2 lone pairs? That would be something like water. Remember, oxygen has 6 valence electrons. If 2 of them are taken up in bonds, that leaves 4, or 2 lone pairs on the oxygen. And this kind of shape is called bent. So the bond angles in water are about 104, 105 degrees. It's based on 109, the tetrahedral angle, but the 2 lone pairs push those bonds together to about 105 degree bond angles. So let's have a look at what happens if we have something like sulfur dioxide. We've got 2 double bonds here, and in this theory double bonds are treated exactly the same as single bonds. We've only got 1 lone pair of electrons here, and we get another bent molecule.